time school, graph transformation 4.50. There are two types of graph transformation we're going to look at: translation 4.51, stretches, compression, and reflection 4.52. Learning objective: to understand the effect of transformation on graph. Y equals fx plus a. That means you're adding a to fx, so therefore you're translating y up. If you say fx minus a, you're bringing y down. So what you're doing is you're raising the graph up if it's a is positive, or you're bringing the graph down if a is negative. So that's vertical translation. Y equals, now you're changing x, you're not changing fx. So because you're not changing fx, you're just changing x, which means you're translating along the x-axis. X plus a just implies that you've got x plus a equal to 0. Therefore, that implies that x equals minus a. So the graph will be shifted to the left. You move the graph to the left because a is minus. You move it to the left by minus a. If it's a is minus 2, you move the graph by minus 2. And that actually has a vector. Sometimes people write it in form of a vector because vector is written as x, y. So that's a vector. In this case, x, y will be equal to, because we're changing x, so it's a minus a. We're not changing y, we're just changing x, 0. So that would be the vector equation for that. But if x minus a, it's a different scenario now. So x minus a, we would have x minus a be equal to 0. Therefore, x will be equal to a. So the vector transformation for that will be a 0. You shift the graph along the x-axis to the right by a. So that's what that is. Y equals, so you got fx now, so that means the whole thing, the whole function, and you're multiplying it by a value. So you're making it bigger. So that means it will go faster and it will become slimmer. So that's compression. So that's large A. That'll be compression. You might have large minus A. It will be compression when A, and reflection. So when A is minus, it's a reflection. But small value of A will be stretches. So you stretch it, so small. A will be stretching it. Fx, F times AX, you're changing X now, you're making it bigger. So instead of a small value of X, you suddenly make it bigger. So you can see you stretch the graph. You basically stretch it. In this case, you're stretching the graph if X is bigger. Or if it's smaller, if you're using 1 over A here, instead of A, if you use 1 over A, it will be compressing this. So I'm thinking about long wave and short waves. Short waves are smaller, so they got 1 over A, and long waves we have AX. So you'll be squeezing them, compressing it. So that's for X. To apply any of the 4 transformations here on quadratic, cubic, reciprocal, to be able to sketch the transformed graphs. Here's an example. You've got a graph of y equals fx, and this is what it looks like. Why does it look like that? Well, because the graph is coming in here and then hit that point, and it's leaving at the same point. So it's coming in there, 1 point. So therefore, if x squared equal to 0, because this is y equal to 0. When y equal to 0, this is what we get. So this is f, that's y equal to 0. So we make it equal to 0, and we square both sides. X equals to 0 twice. X equals to 0 again. So that's twice. And that's why it comes in 1 and leaves second time. Now, then if we change x here, if we add 2 to it, we raise it by 2. The minimum here is 0. And if we raise it by 2, the minimum becomes 2 plus 2. And if we bring it down by -2, that's vertical. You can see that's vertical movement. And then the minimum here is -2. Here is +2. That's -2 because we bring it down by -2. This is horizontal translation because we're not changing fx, we're changing x. So instead of x, which is there, we turn it into x plus 2. So that's x plus 2. So x plus 2 now is what we're dealing with. Again, when we're solving this, we always equate it to 0 because this is y equal to 0. So therefore, x plus 2 squared will be equal to 0, right? Because we're solving it. And what we're solving means we're finding where it crosses the line y equal to 0. So therefore, you square root both sides, so you get x plus 2 equals to 0, and then x equals -2. So the graph will be shift to the left if it's a plus. Because if that's a plus, you're shifting the graph to the left by -2 in this case. And if it's a minus here, you do exactly the same thing. So you get x minus 2 squared equal to 0. You square root both sides, so x equals to 2. Because x equals to 2 twice, because it's coming in once at 2. That's coming in once and leaving at 2 second time. So x equals to 2 twice. So that's the horizontal translation there. So here are some examples on stretches, scale factor. So here we got 1 here. We're stretching or compressing the fx now, not so a times fx. So we're dealing with fx alone here. So you can see if this is the original value, right? X squared. Now we multiply it by 10. So that's the orange. So you can see it slims down, it compresses. Large value compresses it because you make it quicker. It goes faster. And then now we multiply it by 1/10. So you're making it, stretching it, you're making it bigger. Likewise, reflection as well, it's the same thing. We're just reflecting it here, so that's why it's reflected down, but on the line of on the x-axis. So the equation of reflection, y equals to 0, is the line of reflection. So this is the x-axis and it is y equal to 0. So reflecting from here to here. So this is a line of reflection. It's like a mirror. That's the mirror. Now we are reflecting -10, so it's smaller, faster, go faster. And then we reflect it again. And -1/10. So we make it bigger, stretches it, and then reflect it by minus. So that's reflection, stretch, and compression together.